Yes, so now we start the transmission online. Oh, thank you.
Perfect. So let's start. So welcome everyone. So today we have the pleasure to listen to two junior talks. So the first one will be given by Imene Djebour from Nancy, Institut Élie Cartan de Lorraine. And she will speak about local null controllability of a fluid rigid body interaction problem with Navier split boundary conditions. Well, thank you, Imene.
Hello, everyone. First, I would like to thank the organizers, for giving me this opportunity to talk in this seminar. Today, I'm going to present a work that I make during my thesis. It concerns a controllability result of a fluid structure interaction problem. Okay, so we begin by presenting an overview of this kind of problems. So in general, a fluid structure interaction problem describes the evolution of a structure that is in contact with a fluid. For example, in particular, the model that we are interested in today is the following. So we consider rigid bodies immersed in a viscous fluid. So this kind of figure can appear in several applications domain. So here we know that since the structures are moving inside the fluid, it means that the fluid domain is varying with respect of time. Then these kind of problems are free boundary problems. Okay. So here, so the objective of this work is the following. So we can reduce our problem to the following evolution problem. So here Z stands for the velocities of the fluid and the structure. Okay. A represent the position of the solid body. Here, the operator A represents the infinitesimal generator of the linearized system. B is the control operator, and capital F is a nonlinear term. Here, at the second equation, so the operator C represents, in fact, the relation between the position and the fluid velocity. So here, the objective is to consider a distributed control, okay, that is localized in the fluid domain, such that we bring the velocities, so both velocities of the fluid and of the structure to zero, and to control exactly the position of the structure. Okay, so the difficulties that appear in this kind of problem is that are, like we said before, this kind of problem are free boundary problems. It means that our domain is dependent on time. And in that case, we cannot directly apply the controllability theory. Like second, we will use, instead of classical Dirichlet boundary condition, we will use Navier boundary conditions. And we are faced to a nonlinear problem, okay? And finally, these kind of problems are often coupled system. So in many works, the boundary conditions that are considered are the classical Dirichlet boundary conditions that are written as follows. So UF is the velocity of the fluid, and VS here in red is the velocity of the structure. So the Dirichlet boundary conditions means that they are equal at the interface, while the Navier boundary conditions are constituted of two conditions. The first one is called the impermeability condition, and the second is the slip conditions. So here we have the Navier boundary conditions involves the force exerted, the fluid force exerted on the structure interface. Here, beta is the friction coefficient. So n here designates the normal component and 2 the tangential component. So let us analyze, for example, the difference between the two kinds of condition. Let us consider, for example, a fluid domain, okay, that contain a flat boundary. So if we want to write the Dirichlet boundary condition corresponding to that kind of figure here at this flat boundary, since we haven't structure, so the velocity of the structure is equal to 0. So U equal to 0, it means that the velocity of the fluid, it means that the fluid freeze at contact with this part of the boundary. But if we consider, for example, a Navier boundary condition on this part of the boundary, it means that the normal component of the velocity of the fluid equal to 0. It means that the fluid is able to slide. Yeah, it has tangential component not equal to 0 necessarily. Okay, so from the second, from the slip condition, we have that this component is proportional to the force of the fluid that exerted at the boundary. So here we notice that if the coefficient of friction is going to infinity, then the tangential component will be equal to 0. Then we will find the Dirichlet boundary conditions. So the relation between the two conditions is that when the friction goes to infinity, we find Dirichlet boundary conditions. So here we have a motivation to consider Navier boundary condition in this problem. Navier boundary conditions are used especially when we want to study contacts, when we want to study problems near or at contact between the fluid boundary and the structure boundary. For example, in this kind of figure, if we consider a rigid ball inside the fluid and we apply a vertical force, so if we consider Dirichlet boundary condition in that case, there are a recent work that prove in fact that there will be no contact if we consider Dirichlet boundary condition. But if we consider instead Navier boundary conditions, then collision can occur between this rigid body and the bottom and the domain cavity. So here we see that Dirichlet boundary condition can lead to paradoxical results, but Navier boundary conditions are in fact more realistic. So here there are few works that consider this kind of problems. So here we have some existence results. So weak solution to this kind of problem are already done. The uniqueness of the weak solution and the existence and uniqueness of strong solution. So in the latest work. So they are also study of collision. So here are our problem. So we will denote by F the fluid domain. So we consider that the fluid occupies a b-dimensional domain. And we consider a solid S that is immersed in that fluid. Okay. And we consider subsets of the fluid, so which will be our control domain. So here we notice that omega, we consider that we notice that the fluid boundary is constituted of two boundaries, one fixed boundary, and the other is the moving boundary. So here we will the fluid is governed by the Navier stock system that writes as the following. So here we will note U by the, so U will be the fluid velocity, P is the pressure, okay, V is the control, and this function is the characteristic function, okay. So we notice that this system is nonlinear. We have two unknowns. So we have the fluid velocity and the pressure. So T is the Cauchy stress tensor that is defined as the following. And here we notice that this system is written in a moving domain. Okay. Now the structure position is given by the following equation. So here, since the structure is rigid, then the position is given this way. So we have the position at time t and the rotation. So it's a rigid movement. We will note theta by, so the rotation of the solid will be noted by theta and the position by h. So if we derive this equation with respect to t, we found that the structure velocity is given this way, okay, with omega denotes the angular velocity of the solid. So here the equations of the structure motion are given by the balance of linear and angular momentum, okay? So here, since there are some force at the end at the solid interface, so we expect that we have the Cauchy stress tensor appearing in the structure equations. So here we have already a coupled system. So now we write the Navier boundary condition corresponding to our system. So since our domain, since the fluid domain is, the boundary of the fluid domain is composed by two boundaries. So on the fixed boundaries, since we don't have structure, so the boundary condition writes this way. And at the moving boundary, so we need to consider the structure velocity, and the boundary condition will write as the following. So here beta, omega, beta s are the friction coefficients. We complete our system by assuming some initial conditions. So here, here is our system. So the final system that we want to control. So here we have the Navier boundary, the Navier stocks system. Okay. And here we have the Newton's laws, the equation of the structure. And at the boundary, we will consider Navier boundary condition. Okay. So this system is set on a time varying domain. Okay. And time varying domain. And it is a strongly coupled system. Okay. So the objective is to find the control V such that the velocities are equal to 0 at final time t. Okay. So this is our main result. So we can find the friction, assuming that the friction is strictly positive. Then we can find the control such that, so we can bring the velocities to 0 and the position, and we can control exactly the position of the solid. So we have some few results about this kind of problems. So we need we are about to generalize so the results that are made considering directly boundary conditions. Okay. So to solve our problem, so we need to make a change of variable. Then we will linearize the system, the resulting system, and finally we will make fixed point arguments. So change of variable, we will reduce our problem to the final state. There are a change of variable that was already introduced. Then the system will be written as the following. So here, since we made a change of variable, so there are some function that appears in the fluid equations. Okay, the structure equations and the boundary conditions remains the same via this change of variable. So the linearized problem associated to our problems writes as the following. So here we need to prove the null local control, the null controllability of this problem. Okay. So the linearized system writes as the following. Where A is introduced in this work by Wang. So A is a self-adjoint operator. B is, like we introduced before, is the characteristic function. Okay. And we have the following theorem. So our problem is in fact null controllable. Okay, we can find the control such that the velocity and the position equals to 0. Okay, at final time. So to prove this theorem, so we use the theory of Imene, and Takahashi. So the main ingredients here is to prove the observability estimate for the adjoint system of this linearized problem. To prove this observability, we need to prove a Kalman estimate of the adjoint system and to apply the unique continuation property. So the main difficulty of these parts is the Kalman estimate. Okay, and to control the velocity of the rigid body with the fluid velocity, okay? Yes, so we prove, in fact, in our case, that the normal component of the structure velocity is controlled by the fluid velocity over F, over the domain of the fluid, and the tangential component of the structure velocity is controlled by these three terms. So here, if beta s is equal to 0, so we will lose, in fact, the tangential component of the fluid velocity. So we cannot be able to control the whole velocity of the structure. So if we suppose that beta s is equal to 0, then we need to impose that the solid is not a disk. Okay? Is not a disk because in that case, we can control the whole velocity of the rigid body by the fluid velocity, okay? But if S is a solid of any shape, so one need to assume that the friction is positive. Okay, so finally, we make a fixed point argument. So here we recall our system after the change of variable. So one need to control the nonlinear term that appears from the change of variable. So we consider this function, this application, and we need to prove that this application is a contraction, defines a contraction. So we apply the classical Banach theorem. Okay. So finally, in conclusion, so we have proved the null controllability of a fluid-solid interaction system by considering Navier boundary condition at the boundary. So there is some perspective. So so it's very interesting to prove global controllability of this kind of system. Reduce the controls. So it was shown that we can reduce the controls in the Navier-Stokes systems. And one interesting thing is to replace the solid structure by a deformable structure, a beam, for example. So this kind of problem was investigated by Lecoeur, but considering Dirichlet boundary condition. And we wonder if we can do the same considering Navier boundary condition. Thank you for your attention.
So thank you very much. As usual, I'm uploading in the name of all the audience. So thank you for your very nice talk. So if you have questions, you may raise your hand, or you might also open the microphone and ask directly the question, or you can ask the question in the chat, as you prefer. So maybe, well, in the meantime, I will ask one question. So here you are saying that, so sorry, at the end. So you are discussing the case of deformable structure, and well, so from rigid body to deformable structure, there's a huge gap, and probably I would suspect that you could be able to get a null controllability result if the structure evolves into a finite dimensional deformation, right?
Yes, that was the idea of Lecoeur. In fact, he disguised the structure in order to to control the structure velocity with the fluid velocity.
But the structure is finite dimensional or is it infinite
No,
dimensional?
he discretized it.
Ah, okay.
So he just some points of the structure of the beam.
Here, it would change. Would it strongly change the approach, or could you try to approach this idea to your case?
So honestly, I didn't try it, but maybe it could work with Navier boundary condition. So it's very interesting to try this problem.
Okay, thank you. Are there any other questions?
Yeah.
Enrique?
Yes, thank you. Thank you very much for your presentation. It was very nice. And also at the end, you have spoken a little bit, you have talked about the global controllability.
Yeah.
Well, there is a result by Coron, Marbach, and
Okay.
anyone else that prove global controllability of Navier-Stokes equations with Navier conditions. So do you think that there is something to take profit of it for this problem, for fluid structure? Can you say something on the strategy that could be used in this case?
Here in our theory, so in fact that to make the fixed point work, we need that the initial condition is small enough. So I think that it's a little bit hard for me to prove global controllability in this case. But I will see what Coron Marbach did for proving global controllability and try if we can generalize the result. But I think that so.
Okay, okay. There is Frédéric Marbach that is speaking about it. Maybe let him speak.
Okay.
So Frédéric, is your microphone? Yeah.
Hi, thank you for your talk. So maybe we can discuss later about what we can do for global controllability. But I read in your paper that you say it's probably tough, and maybe you're right. The question I was asking myself is why do you need beta S positive? What do you want to? What can you say?
So this problem. So this estimates, in fact, are essential in the elaboration of the Carloman estimate. Okay.
And in the case beta S equals 0, do you expect that something strange happens, like the system is not controllable, or is it just a technique that does not work?
If beta S is equal to 0, we can have the null controllability by. But we need to impose that S is not a disk.
Okay.
Yeah, it's not a disk because if S is not a disk, so we have more than this estimate.
Okay.
The whole, if S is not a disk, so we have that the whole structure velocity is controlled by the fluid velocity, okay? If S is not a disk, but if S is of any shape, so we need some complementary estimate, and we need that beta S is strictly not equal to 0 in order to control the disk.
Okay, thank you. Sorry, thank you.
Yeah.
Okay, is there any other question? Okay, so if not, so there's one, sorry, by Kristen Montoya. Maybe you can try to extend your results adding a heat equation.
Yes, there are results of Takahashi and Roy. They proved controllability of the same kind of problem with Dirichlet boundary condition and adding the heat equation, the Boussinesq system, right? So it's called Boussinesq system. And I think that adapting what they have done, I think that we can have same results. Yes. Yes. I believe that we can extend.
Okay. So is there any other question? Last chance? Well, okay. So otherwise, well, let's thank again Imene for a nice talk. And so we will take a few seconds break to switch speakers.
Okay.
Well, thank you again, Imene. And please also send me your slide so that
Okay.
I can upload it on the web afterwards.
Okay, no problem. No problem.
Yeah. So I think you should, yeah, probably stop the share screen. Yeah, perfect.
Thank you.
Thank
Bye,
you.
everyone.
And Esteban, so if you want to share your screen, in principle you can. I hope so.
Okay, this one.
Yes. Can you go full screen? Yeah, perfect.
Okay. So.
Okay, so let's continue. So the next speaker is Esteban Hernández from Chile. From his Universidad in Valparaiso, right?
Yeah.
Yeah. So he will speak about rapid stabilization of an unstable heat equation and the boundary disturbance. Well, thank you, Esteban.
Thank you for the introduction. Also, I want to thank to the organizer for giving me the opportunity to present this work here. Also, before we start this talk, also I want to mention that this is a joint work in collaboration with Patricio Guzmán from Universidad Santa María in Valparaiso. And also I want to mention that this work is part of my thesis work, which is under supervision of Eduardo Serpa from Universidad Católica de Santiago de Chile and Christophe Prier from the Grenoble Alpes University. So, the main outline of this talk, in the first part, we are gonna state the problem we want to study here, then going to the feedback design to give some insight about this, and then a small review about the well pose of the closed loop system. By the end of this presentation, I'm gonna show some numerical simulations in order to illustrate our theoretical results. And in the last part, we has some remarks and important comments. Okay, so we are gonna consider this one-dimensional unstable heat equation with Neumann control here, with the state is denoted by Z. We have also this coefficient A, and which is continuous. As usual, the control is U, and in this case, we are gonna consider D as an unknown disturbance affecting the system in the boundary. So, in general words, the main goal of this work is to design a feedback control law which achieve a rapid exponential stabilization even in the presence of this unknown boundary disturbance. So, okay, so before to go to the feedback design, I would like to also mention another kind of method, different that I'm going to use. Deal with the stabilization problem in presence of uncertainties in PDEs is an important topic in control also. So there is at least two very popular methods. The first one is called adaptive control, and usually is used when we have some unknown parameters in the system. And the other one is the active disturbance reaction control, which is used when we have external disturbance acting on the system. The main idea, for example, in adaptive control is try to estimate in some way the unknown parameters and then design a feedback law. In the other method, in active disturbance reaction control, usually we have to put a lot of effort into try to estimate the disturbance, and then using this estimation usually is the idea is to cancel the action of the disturbance. The method we propose here is a little different because we are gonna combine the well-known backstepping method and the use of the multi-evaluate operator sign. So our feedback design here is the idea is separate the control in two parts. The U1 is the part we deal with the instability caused by the presence of coefficient A, and the second one, U2, is the part of the control we deal with the boundary disturbance D. So now we are gonna to design the U1. For design U1, we are gonna use the backstepping method, which is given here by equation 3. And the gain kernel is the solution of the equation 4, where here is here the parameter A, and this parameter omega can be choose larger as we want. So, and this parameter fix also the exponential decay of the target system. So, with that, it's well known that the backstepping method take the system 5 here and map into this system, which is exponentially stable with parameter omega. Okay, so from that we choose U1 in this way, given here by 7. So now we are gonna design the U2 part of the control. So to do that, we plug the control the part U1 into the original control system, and then we apply the backstepping transformation, and we arrive to this equation given by 8. Here we have the second part of the control, U2, and the disturbance. So now here, we are gonna multiply this equation by y, and then perform an integration by parts, and we obtain here 9, this equality 9. So this part of the equality can be seen as the evolution of the L2 norm here. And the question here is how to design U2 in order to ensure that this part of the equality be negative, okay, at 0 or negative. So to solve this, we choose U2 in that way, given by 10. U2 is equal to minus capital D sine of the y at L, where capital D is a constant positive, and sine is the multi-valued operator here given by 11. Okay, so at this point, it's necessary also to do some assumption over the disturbance and the constant D here, we assume that this constant capital D is a bound for the disturbance. So with these two things, we are able to ensure that that part of this equation is negative, and then it's easy to see that energy decreases exponentially with parameter omega. So summarizing, our feedback design in variables C is given by 13, which this first part is the given by the backstepping method, and which deal with the instability caused by the parameter A, and this part of the control reacts the action of the, the effects of the disturbance affecting the boundary here, okay? So here we have the system in closed loop. Now let's note that this system is not any longer a differential equation. We have here a differential inclusion. So in order to prove the well pose of this system, we will need the theory of maximal monotone operator. So to begin with that, we apply the backstepping method, the backstepping transformation to this system 14, and we arrive to this system 15 here. We have here the parameter of the decay, and here we have the disturbance. So the next step is to move the disturbance from the boundary to the domain. To do that, we use a change of variable, and where phi is lead function. So we are able to rewrite the system 15 into the system 17 here. And this part F is given here. It depends on the derivative of the disturbance, but in this case has the role of the disturbance. So now we put effort into prove the well pose of this system. So to do that, we are gonna consider the following operator, capital A, defined by 19 here. Capital A, P is equal minus second derivative of P plus omega P, where the domain of this operator is described by this, this set. The elements in H2 such that the derivative at 0, 0, and in the right boundary, we have this inclusion. So one important thing is here is the operator capital A is not linear. And that is in virtue because the domain is not a linear subspace in virtue of the presence of the sign operator. So this operator cannot be linear. So here we have also in a more compact notation, the closed loop system. So in order to prove the well pose of this system, we need to prove first the operator capital A is a maximal monotone operator. Okay, and to do that, we use the Minsky theorem. It says the capital A is a maximal monotone operator if and only if one thing is A is monotone, and the second one, if for any F in L2, there exists at least one element which satisfies this equation, okay? That is a condition over the rank of capital A. So for our case, to get the monotone part is an straightforward computation, and also in some part we have to use the fact of the sign multivalued operator is also a monotone, maximal monotone operator. For the second part, we need a little more analysis. And to study this equation, we consider here this functional capital A, which is defined over H1. And we have here this term, which is a phi lambda phi lambda is the raw regularization of the function phi here, given by capital D absolute value of x. So the spirit of this functional is this integral part give us the equation in the domain, and the other part of the functional allow to obtain the boundary condition for the solution. So from now we denote d sine x as alpha, and alpha lambda will be the Rosida approximation of alpha. So with regard to this functional, we are able to prove the following lemma, which says for any lambda positive and for any f in L2, there exists at least one minimizer for this functional j, which this functional lies in H2, and also is solution to this problem 23, okay, which is an approximation problem of the thing we want. So moreover, this minimize also satisfies this set of inequalities. So finally, after that, it can be proved that the sequence of minimizers indexed by the parameter lambda converge to an M solution of this problem 27 here, when lambda is going to 0. So this allows to conclude that capital A is a maximal monotone operator. So far we have the maximal monotone operator, and we are in position to continue with the proof of the well pose of the closed loop system. So to do that, we need to do a second assumption over the disturbance. Here, we are going to assume the disturbance has this regularity, belongs to the space W21, and D at 0 is 0. With this assumption over the regularity of D, we can able to ensure that F satisfies this regularity, and then by using the Kato theorem, which is here in the screen, we are able to conclude that for any initial condition in the domain, there exists a unique solution W with this regularity to our closed loop system. So now, using again the changer variable, we can conclude the same thing for the system 29. For any initial condition in the domain of the operator, there exists a unique solution with this regularity solution to the closed loop system, okay? And finally, in order to get the well pose in the control system in variable C, we use the inverse of backstepping transformation, which is given by 30, is a very explicit formula, with the kernel solution to this equation here. And this allows to conclude that for any initial condition which satisfies this condition, this is the set of admissible initial condition for the problem. We have a unique solution with this regularity solution to the closed loop system. So finally, the exponential decay of this solution follows from the continuity of the backstepping method and also from the inverse. So there exists C1 and C2 constant bigger than 1, and we have this inequality 34, which ensure the exponential decay with parameter omega of the solution C. So here, in order to illustrate our results, we have here the system without control perturbed in the boundary here, and also we plot here the evolution of his L2 norm, the energy. And now we consider the action of the control, which is represented by this part. This part is the reactor of the disturbance. We have here the state, and also we plot here the energy of the solution. So to summarize this talk, in this talk, the rapid exponential stabilization problem for an unstable heat equation under boundary disturbance was solved. The control design proposed here is a combination of the backstepping method and the suitably use a multi-valued operator sign. The well-possessness of the closed loop system was proved by using the theory of maximal monotone operators. And also we performed some numerical simulation in order to illustrate our results. So that is all. So thank you for your attention.
Well, thank you, Esteban, for your very nice talk. I'm applauding for the name of all the audience, as usual. So is there any questions? So again, if so, you can ask the question directly or write it in the chat as you prefer, or raise your hand if you know how to do it. Okay, we can do it that way too. Please, Luz.
Do you have an idea if you can do this in the n-dimensional setting? Because everything, I think that the techniques are one-dimensional, no? And I don't know if you can do this in Rn in general, the heat equation in Rn.
This is a problem we are discussing with Patricia already and trying to, because we don't have a, I don't know the backstepping method in more higher dimensions. So we have to change the method to stabilize this part. So.
Okay, thank you very much. I think it's a nice problem. Enrique.
Yes, Enrique.
Thank you very much for your talk. It was very nice. My question is if you can say something for less regular disturbances.
Less regularity. Okay. The thing is we need so high regularity in the disturbance is because in some part of the demonstration we have to move the disturbance from the boundary to the domain. I don't know if we can try about that things. I think we can admit some less regular assumption over the disturbance, but by the moment I don't know how to solve that.
Okay.
This approach, I mean.
Are there any other questions? So, okay, in the meantime, if I may, I have a question considering your choice of the sign function. So I remember that it's done in the choice of U2. Can you go back to this slide, please?
Yes, of course. Here. This one, or
yes, yes. So in this one, what I don't really get is that you have this term minus the norm of yx in L2 square, which should help you, right?
Yeah.
And somehow this term controls y of TL square, right? Boundary. No?
I'm sorry.
Yes, but you have dy. Okay. So it controls y square, right? YTL square. But of course, on the other hand, you have d times y. Okay. So no, I was a bit surprised because of that term, which is never used, but in fact, it's quadratic, while the others are linear. So that's okay. Yeah, sure. And also in the same spirit as the question by Enrique, I wonder if you could, by density, be able to define solutions for disturbance which are only in L infinity, because it seems that somehow you should have a decay of your solutions for D which are in a bounded set of L infinity, right? I mean, when I'm looking at this design, it seems that as soon as D is bounded by capital D, then I will have the decay of some norm among the as the time evolves, right?
Mm-hmm.
So, well, I wonder if you could try some kind of density argument to be able to define the solutions for D which are simply in L infinity. But I'm not a specialist on this question.
I'm not sure how to do that, because the assumption of over the regularity of D is just to satisfy the assumption of the cathode term. So if we can improve something there, I think we can. Choose a less regularity for the disturbance. But
yes, but Kato theorem is a very general theorem, right?
Mm-hmm.
And here you are you have a specific operator for which you have some nice decay properties with only L infinity bounds on D, right? So
Yeah.
I don't know, but maybe there are some ways to do that, and I would suspect it would be natural.
Mm-hmm.
But it's only well, it's mainly a comment, because in fact I don't know how to do it. It's probably delicate.
Yeah, I mean, so I have to study more this.
Okay, are there any other question? So again, you can raise your hand or write in the chat, right, if you feel more confident to that. Okay, so let's stop here then. Well, thank you again, Esteban, for this very nice talk. And also, please, if you agree, can you please send me your slides so that I can upload them on the web and make it available to everyone?
Okay.
Well, thank you.
Okay, bye-bye.